Hey everyone, welcome to The Explainer. Today, we're diving straight into the gritty engineering reality of electrolytic capacitors. You know, if you've ever designed a circuit, or let's be real, debugged a literal smoking power supply, you already know these things aren't just simple energy buckets on a schematic. No, they're actually complex, highly dynamic electrochemical systems. Let's get into it.
Which brings us right to a somewhat explosive question. Why exactly do electrolytic capacitors explode? It's a super high-stakes question, right? And yeah, we're kicking things off by looking directly at the dramatic end state of component failure. Because honestly, understanding exactly how and why these devices fail in the real world, that is absolutely the key to stopping it from happening in your own designs.
I love this quote from our source material. Electrolytic capacitors are often the clock that determines system life. Man, that's not just a casual observation, that is senior-level insider knowledge right there. If you want to guarantee system reliability, you have to realize that this specific component is constantly ticking down. And your design choices, they entirely dictate just how fast that clock runs.
Okay, let's dive into this. Here's our roadmap to unpacking all this. We're gonna hit 1. Anatomy of a failure. 2. Physics of high-density storage. 3. The thermal death spiral. 4. Polymer and hybrid solutions, and finally 5, engineering selection and trade-offs.
All right, starting with number 1, anatomy of a failure. Because to truly grasp why these components fail out there in the field, we first got to look at what's actually going on inside them. So, when we break down the fundamental layers of a wet aluminum electrolytic capacitor, we're looking at a few key things. An etched aluminum anode foil, an incredibly thin aluminum oxide dielectric layer, a liquid electrolyte cathode, and a separator paper spacer. Now here's a wild detail that actually trips up a lot of folks. That liquid electrolyte, it actually functions as the effective cathode. It creates this conductive path deep into the microscopic pores of the aluminum. Pretty cool, right? And this brilliantly illustrates what engineers lovingly call the jelly roll construction. Look at how all those delicate layers we just talked about are tightly wound together and sealed up inside that little aluminum can. It really takes all that abstract chemistry and grounds it right into the physical, three-dimensional component you actually solder onto your board.
Moving on to part 2, physics of high-density storage. Like, how exactly do these relatively tiny cans hold such massive amounts of electrical charge?
Well, it all comes back to the classic parallel plate capacitance formula. You know it. C equals epsilon A over D. So to maximize capacitance, you need massive surface area, that's your A, and you need minimal separation distance, your D. By chemically etching the aluminum, manufacturers are creating millions of microscopic tunnels, which massively increases that surface area. And then, the anodization process grows an insulating oxide layer that is literally nanometers thick, completely minimizing the distance. It is just an absolute triumph of microscopic engineering.
Now for part 3, the thermal death spiral. Brace yourselves, because this is exactly where that ideal, perfect schematic symbol you draw on the whiteboard slams right into harsh, unforgiving real-world physics. Let's walk through how this builds into a completely terrifying positive feedback loop. Step 1. High ripple current flows through the capacitor. Step 2. That current hits the equivalent series resistance, or ESR, which causes power dissipation as heat, good old I²R losses. Step 3. Internal heating rises. Step 4. That heat actually causes the liquid electrolyte to evaporate and slowly escape through the rubber seal over time. And Step 5. With less electrolyte, the ESR increases even further, which takes us right back to Step 1, generating even more heat. It is a vicious, inescapable cycle ending in inevitable failure.
So, the absolutely crucial point here is this rule of thumb, the Arrhenius 10-degree rule. It states that the estimated lifespan of a non-solid electrolytic capacitor halves for every 10 degrees Celsius increase in internal operating temperature. Literally halves. You need to burn this mathematical relationship into your memory right now. It is a core tenet of component reliability. Just look at how incredibly fast that lifespan drops across these temperature points: 85 degrees, 95 degrees, and 105 degrees. If you push your thermal budget from 85 to 95 and then up to 105 degrees, whether that heat is coming from a hot ambient environment or from your internal ripple current, your capacitor's life practically vanishes. You are quite literally burning away your operating hours. Okay, on to part 4, polymer and hybrid solutions. Because engineers, thankfully, didn't just accept this thermal fate. let's shift our narrative to the real engineering heroes of this explainer, the advanced materials created specifically to solve these nasty dry-out and ESR problems. Now, what's really interesting about this trade-off is how it all hinges on the electrolyte. Pure wet aluminum, it gives you high ESR and a definite dry-out risk, sure, but it has this fantastic self-healing ability. Solid polymers totally replace the liquid with a conductive polymer, giving you ultra-low ESR and zero dry-out, but they completely lose that self-healing magic. So what about hybrids? Well, they mix both. They give you incredibly low ESR, a greatly reduced dry-out risk, all while preserving that vital self-healing mechanism. It's just a brilliant engineering compromise. And here's how that hybrid construction actually works in practice. The solid conductive polymer is combined with the liquid electrolyte that impregnates the spacer. The polymer provides the incredible conductivity you need for low ESR, while the liquid is just kind of hanging out there to provide oxygen. If a micro defect occurs in the aluminum oxide layer, say from a random voltage spike, that liquid facilitates localized hydrolysis. It releases oxygen to immediately, effectively heal and reform the dielectric. Check out the real-world stability data alongside this surface mount hybrid cap. The performance charts show the ESR remaining completely flat and rock-solid stable over 5,000 hours of continuous operation. No joke. These components can maintain an ultra-low ESR. We're talking sometimes down to 3 milliohms, even under extreme ripple currents. They easily outlast standard wet electrolytics by an absolute mile. Finally, Part 5. Engineering selection and trade-offs. Because knowing the physics is honestly only half the battle, right? Applying it to practical, real-world product design, that is what separates the novice designers from the senior engineers.
Let's contrast two classic power supply designs to see this in action. A linear power supply operating at 100 Hz primarily needs massive bulk capacitance just to smooth the mains voltage. But a switched-mode power supply, or SMPS, operating at 100 kHz or more, that plays by entirely different rules. At those high switching frequencies, standard wet capacitors are just way too resistive and inductive. High-frequency switching absolutely demands polymer or hybrid technology for their ultra-low ESR and ESL, or equivalent series inductance.
And here is the exact equation proving why. In high-frequency SMPS outputs, the ripple voltage is actually dominated by the equivalent series resistance, not the capacitance itself. The math is beautifully simple. Delta V out is approximately equal to the ripple current times the ESR. So at these high frequencies, the internal resistance of your capacitor matters way more than its actual storage capacity when it comes to smoothing out that voltage rail.
To summarize our ultimate insider knowledge, let's review these selection insights. For automotive EV systems or harsh aerospace environments with crazy vibration and temps over 125 degrees, use hybrids. For budget consumer electronics where you just need bulk energy storage, wet aluminum is still king. For high-speed telecommunications power supplies, go with solid polymer. Ultimately, high reliability design means planning for ESR drift and derating carefully. Trust me, planning for non-ideal behaviors early saves you from late-stage surprises and incredibly costly field returns down the road.
Which brings us to a final, slightly provocative thought. Next time you look at a schematic, are you going to see an ideal, perfect capacitor or a thermal clock ticking down? Understanding the physical, electrochemical reality behind that tiny symbol on your screen changes how you design forever. Thanks for joining me for this explainer. Keep these realities in mind and happy engineering.